An autotransformer is a type of transformer that has only one winding, which is common to both the primary and secondary circuits. The winding is divided into two parts, with the primary part connected to the voltage source and the secondary part connected to the load. The voltage difference between the two parts of the winding determines the voltage transformation ratio. Advantages of autotransformers include: firstly, smaller size and lower cost compared to conventional transformers; secondly, lighter weight; thirdly, higher efficiency; and fourthly, stepless voltage regulation. Disadvantages of autotransformers include: firstly, a galvanic connection between the primary and secondary circuits, and secondly, limited voltage transformation ratios. Other types of transformers include the following. 1. Isolation transformer. An isolation transformer isolates the primary and secondary circuits from each other. There is no galvanic connection. They are used for safety and noise reduction. 2. Current transformer, or CT. A current transformer is used to measure current in high voltage circuits. It is a step-down transformer that converts high current to a low current suitable for measurement. 3. Potential transformer, or PT. A potential transformer is used to measure voltage in high voltage circuits. It is a step-down transformer that converts high voltage to a lower voltage suitable for measurement. 4. Distribution transformer. Distribution transformers are used in power distribution networks to step down high voltage such as 11,000 volts to low voltage such as 230 volts for use by residential and commercial customers. 5. Welding transformer. Welding transformers are designed for welding applications. They provide a high current at a low voltage suitable for welding. 6. Buck-boost transformer. A buck-boost transformer is a step-up or step-down transformer used to provide a slightly different voltage than the source voltage. 7. Saturable reactor transformer. Saturable reactor transformers are used as a variable inductor in power electronic circuits. The saturation characteristic allows for control of inductance and current flow. Autotransformers offer several benefits. Their compact size and reduced material requirements translate to lower production costs compared to traditional two-winding transformers. The lighter weight of autotransformers makes them easier to handle and install. Due to the direct electrical connection between the primary and secondary windings, autotransformers exhibit higher efficiency, minimizing energy losses during voltage transformation. The ability to adjust the voltage ratio continuously provides flexibility in matching the load requirements. However, autotransformers also have drawbacks. The direct electrical connection presents a safety concern, as there is no isolation between the high voltage and low voltage circuits. This lack of isolation limits their use in applications where safety is paramount. The voltage transformation ratio is restricted by the single winding design, making them unsuitable for applications requiring large voltage changes. Isolation transformers are designed to provide electrical isolation between the primary and secondary circuits. This isolation is achieved through separate windings that are not electrically connected. By preventing direct electrical contact, isolation transformers offer enhanced safety by eliminating the risk of electric shock. They also block the transfer of electrical noise and interference from one circuit to another, resulting in cleaner power. Current transformers are specialized transformers used to measure alternating current flowing through a conductor. They step down the high current to a lower, measurable level while maintaining an accurate representation of the original current. Current transformers are essential for monitoring and protecting electrical equipment in high current applications. Potential transformers are designed to measure high voltage levels by stepping them down to lower, safer levels. They provide an accurate representation of the original voltage, allowing for precise measurement and monitoring. Potential transformers play a crucial role in power systems by enabling the safe and reliable measurement of high voltages. Distribution transformers are widely used in power distribution networks to step down high voltage electricity from transmission lines to low voltage levels suitable for residential, commercial, and industrial use. These transformers are essential for delivering electricity safely and efficiently to end users. Welding transformers are specifically designed to provide the high current and low voltage required for welding processes. They offer the necessary power characteristics for creating strong and reliable welds. Buck-boost transformers are versatile transformers that can either step up or step down voltage by a small amount. They are used to compensate for voltage fluctuations and ensure a stable voltage supply to sensitive equipment. Saturable reactor transformers utilize the principle of magnetic saturation to control the flow of alternating current. They are used in various applications, including voltage regulation, current limiting, and power control. When selecting a transformer, it is important to consider several factors including voltage ratio, power rating, isolation requirements, efficiency, and application-specific requirements. The voltage ratio determines the relationship between the primary and secondary voltages. The power rating indicates the transformer's ability to handle a specific amount of power without overheating or failing. Isolation requirements dictate whether electrical isolation between the primary and secondary circuits is necessary for safety or noise reduction. Efficiency measures the transformer's ability to convert electrical power from the primary to the secondary circuit without losses. Application-specific requirements such as size, weight, and environmental conditions should also be considered. Transformers play a critical role in modern electrical systems, enabling the safe and efficient transmission, distribution, and utilization of electrical power. From stepping down high-voltage electricity for household use to providing isolation for sensitive electronic equipment, transformers are essential components in a wide range of applications. Understanding the different types of transformers and their characteristics is crucial for selecting the right transformer for a specific application. This knowledge ensures optimal performance, safety, and reliability of electrical systems. When working with transformers, it is important to follow all safety precautions and guidelines. Transformers can operate at high voltages and currents, posing a risk of electric shock and other hazards. Always disconnect the power supply before working on a transformer. Use appropriate personal protective equipment such as gloves and safety glasses. Inspect transformers regularly for signs of damage or wear. Ensure proper ventilation to prevent overheating. If you are not qualified to work on transformers, seek assistance from a qualified electrician. Proper installation and maintenance are essential for ensuring the safe and reliable operation of transformers. Follow the manufacturer's instructions for installation, wiring, and grounding. Inspect connections regularly for tightness and corrosion. Clean transformers periodically to remove dust and debris. Monitor transformers for signs of overheating, vibration, or unusual noise. If you notice any problems, consult a qualified electrician. Transformers are designed to operate within specific voltage and current limits. Exceeding these limits can damage the transformer and create a safety hazard. Ensure that the transformer is properly sized for the load it is serving. Avoid overloading the transformer, which can cause overheating and premature failure. Use appropriate overcurrent protection devices such as fuses or circuit breakers to protect the transformer from damage due to overloads or short circuits. Transformers can generate heat during operation. Proper ventilation is essential to prevent overheating and ensure reliable operation. Ensure that the transformer is located in a well-ventilated area. Avoid blocking the ventilation openings in the transformer enclosure. If necessary, provide additional cooling such as fans or air conditioning. Transformers can be affected by environmental conditions such as temperature, humidity, and altitude. Choose transformers that are designed for the specific environmental conditions in which they will be used. Protect transformers from exposure to extreme temperatures, humidity, and corrosive substances. Consider the altitude when selecting transformers, as higher altitudes can affect the transformer's cooling capacity. Transformers are essential components in many electrical systems, and their proper operation is crucial for safety and reliability. By understanding the different types of transformers, following safety precautions, and performing regular maintenance, you can ensure that your transformers operate safely and efficiently for many years. Always consult with a qualified electrician for any questions or concerns about transformers. Transformers are mature technology, but ongoing research and development are leading to new innovations. These innovations include more efficient transformer designs, improved insulation materials, and advanced monitoring and control systems. These advancements are helping to improve the performance, reliability, and sustainability of electrical systems. The efficiency of a transformer is defined as the ratio of output power to input power. Higher efficiency transformers consume less energy and reduce operating costs. Transformer efficiency is affected by factors such as core losses, winding losses, and load. Core losses are caused by hysteresis and eddy currents in the transformer core. Winding losses are caused by the resistance of the transformer windings. The load on the transformer affects both core losses and winding losses. Transformer insulation is essential for preventing short circuits and ensuring safe operation. Transformer insulation materials include oil, paper, and epoxy. The insulation must be able to withstand high voltages and temperatures. Transformer insulation can degrade over time due to factors such as heat, moisture, and contamination. Regular inspection and testing of transformer insulation are essential for preventing failures. Transformer monitoring and control systems can provide valuable information about the transformer's condition and performance. These systems can monitor parameters such as voltage, current, temperature, and oil level. They can also provide alerts when abnormal conditions occur. Advanced monitoring and control systems can help to improve transformer reliability, reduce maintenance costs, and extend transformer life. Transformers are a critical component of the electrical grid, and their reliability is essential for ensuring a stable and reliable power supply. Transformer failures can cause power outages, equipment damage, and safety hazards. Therefore, it is important to implement a comprehensive transformer maintenance program. A transformer maintenance program should include regular inspections, testing, and repairs. Inspections should include visual inspections, oil analysis, and electrical testing. Testing should include insulation resistance testing, turns ratio testing, and excitation current testing. Repairs should be performed by qualified technicians. By implementing a comprehensive transformer maintenance program, you can reduce the risk of transformer failures and ensure a stable and reliable power supply. Transformers are also used in many industrial applications, such as motor control, power supplies, and welding. In these applications, transformers are used to step up or step down voltage to match the requirements of the load. Transformers used in industrial applications must be rugged and reliable to withstand the harsh operating conditions. Transformers are also used in electronic devices, such as computers, televisions, and mobile phones. In these devices, transformers are used to convert voltage from the power outlet to the voltage required by the electronic components. Transformers used in electronic devices must be small and efficient. The selection of a transformer depends on the specific application. Factors to consider include voltage ratio, power rating, isolation requirements, efficiency, size, weight, and cost. It is important to consult with a qualified electrical engineer to select the appropriate transformer for your application. Transformers are a vital component of modern electrical systems. By understanding the different types of transformers, their characteristics, and their applications, you can ensure the safe and efficient operation of electrical systems. Always follow safety precautions when working with transformers, and consult with a qualified electrician if you have any questions or concerns. Transformers will likely continue to evolve to meet the changing needs of the power grid and other applications. This evolution will likely focus on improving efficiency, reducing size and weight, and enhancing reliability. As the demand for electricity continues to grow, transformers will play an increasingly important role in ensuring a stable and reliable power supply.